back too? Yes, thank you. Hi, welcome to another lecture on Markov decision processes. These announcements are the same as last time, so we won't go over them. But today we're going to continue talking about MDPs. So last time we managed to actually define what on earth MDPs are. Today we're going to start talking about how to actually solve these. As a quick recap, MDPs were basically like search problems, but search problems where we weren't really sure what the consequences of our actions were going to be. So in regular search problems, you're in a state, you take an action, you know where you're going to end up. We relaxed that assumption in Markov decision processes. So we basically looked at systems that there were a set of states. There was an initial state as 0. From every state, we could take certain actions, like try to go north, try to go east, and so on, exit. And the only tricky part was that whenever we try to take an action, if we're in state S and try to take an action A, we wouldn't necessarily end up in S prime, right? There was some probability distribution over the possible states where we might end up in. And that's different from a search problem. In a search problem, basically what was happening is there was one S prime for which this probability was 1, and it was 0 for all the other states. Now here we have a distribution over possible states we might end up in. And then we had rewards, or costs, that were associated with every transition. So if I were in state S, I took an action A, and that action resolved itself to me being in S prime. That 3-tuple is associated with some reward. And we saw some examples of this. We looked at a grid world, and in the grid world, we'd start at some state, we could go up, down, left, right, and we had some living reward, some penalty maybe that we were paying at every step that we were taking in certain cases. That could be 0, that could be negative, maybe that's positive. We had a pit of fire. When we were in the pit of fire, we had to take the exit action and incur reward -1, so a big cost there. And we had a gem, and in that gem, we could take the exit. When we were in that position that had that gem, we could take the exit action and get a reward of +1. We also saw the racing example, right? So for the racing example, we could be either warm or cool, and we could drive fast or slow, and at some point we might end up overheated. And then during a little quiz, we also saw something really simple, an MDP that is like grid world that looked like that on the lower right of that slide. And what happened with this MDP is that we had states A, B, C, D, or E, and we had rewards associated with some of these. We had no uncertainty, right? So the transition model was deterministic, and we said if I'm in state A, I have to take the exit action, and then I get a reward of 10. And if I'm in state E, I have to take the exit action, and then I get a reward of 1. And there was one suggestion, and this is why I want to come back to this. There was one suggestion from one of you who said, well, maybe the optimal thing to do here is to first collect one of these rewards and then go and collect the other, right? And I wanted to kind of clarify, go over again, and make sure that we all understand why that's not the optimal thing to do. And it's not the optimal thing to do for a few reasons. One of them is more like a technicality, so let's say that and get it out of the way. The technicality is that the way we defined this MDP was that once I'm in A or in E, I have to take the exit action. There's no other actions available to me. And I take the exit action, and so I'm now in the null state, and I'm done. So I can't take both 1 and 10. But that's more of a technicality. The biggest thing is that if you think about this, reward in MDP is not some sort of treasure that's there. And once you visit that state or go out of that state, you remove the treasure and take it with you, right? And then walk away. The rewards in MDPs are associated with transitions. So if we define this MDP to be, for instance, that when you get to state A, you don't have to take the exit action. You can actually go right. Maybe there's no more exit action. You can go right and end up in B. Right? And if we associated a reward that said, whenever you're in state A and take action right and end up in B, that's when you get a reward of 10. what would the optimal thing to, and we did the same, the equivalent thing for state E, what would the optimal thing to do in that MDP? Would it be to go and visit E and then go and visit A? Or would it be something else? What do you think? So if I define an MDP where I don't have to exit anymore, I can just, if I'm in A, I can go right and collect my reward of 10. If I'm in E, I can go left and collect my reward of 1. What's the optimal thing to do? Yeah? Keep visiting A, right? You go to A, and then you go left, and then you go to A again, then you go right, then you go to A again, then you go right again. And you keep on getting that reward, right? Because that reward is associated with this transition that says, if I'm in A, and if I take action right and end up in B, I get 10. So clearly what I should do is just keep on doing that, right? And so that's if you wanted to have a Pac-Man-like world where you do have treasure, and the treasure does disappear, so it's like food pellets that you can eat, right? And each time you eat a food pellet, you get some bonus points. That's a different MDP. What is the state space for that MDP? What do we define the state space to be when we have treasure in the world in particular positions? We talked about this when we talked about just the state space representation for that search problem. So assume I have deterministic actions, so that means that I am actually in a search problem. What do I do to make it such that my rewards are still associated with states, but that whenever I visit a state, I essentially collect that treasure, and that treasure is no longer available next time? What if I augment my state space? What if so right now if my states are A, B, C, D, and E, there's really no way to represent that once I visit A, that 10 is gone, right? Because that 10 is associated with a transition. What if I augmented my state space to say, my states are not just A or B or C or D or E, my states are actually gonna describe where treasure is on this map. So the state doesn't just say what the position of the robot is, the state also says which positions on the map still have reward and what the reward is. So a state could be, I am in B, and there's a 10 reward at A, and there's a 1 reward at E. And now my transition function is different. The transition function basically says, whenever I go in A, if there was reward, if there was treasure in A, the state that I then transition to removes that. Right? And that's how I can actually capture the fact that there's treasure that I can get to, I can eat it up, I can consume it, and it's no longer there. And I can try to search in that MDP, and in that MDP, it might very well be that the optimal thing to do is to go for the one treasure and then go for the next treasure as long as the game doesn't end, right? But important thing to note is that rewards are associated with transitions. Every time you hit that transitions, you get that reward. And we assume the Markov assumption here. We assume that the current state describes everything you need to know. Everything that will happen from now on is independent of what happened in the past, conditioned on the current state. So the current state really needs to capture everything that you've done if what you've done is actually relevant to what's going to happen in the future. So I just wanted to take that little break and make sure that we're on the same page with that. Any questions about that? Good, so this is what MDPs are. Now, how do we actually solve them? How do we find what actions to take in each state? That's the topic for today. And going back to the racing example, we talked about particularly simple MDP that's kind of handy because we can actually do calculations by hand on this. But essentially, we had a car, it could be cool or it could be warm. And when it was cool, it could drive slow or it could drive fast. And if it drove slow, it would stay cool. If it drove fast, it could either stay cool or it could become warm, right? And so you can write out the search tree, and it looks something like this, at least up to level 2. But the problem is that it doesn't stop there. You can keep on, whenever you're in cool, you can decide to go slow or decide to go fast. And it just keeps going and going and going. Whenever you're in warm, you can decide to go slow or you can decide to go fast. And so if you try to run something like expecting max on this, which is what Peter showed you a couple lectures ago, it's going to be doing a ton of work because of two reasons. One, you see the same states again and again. Every time you end up in blue, the same thing happens. You can go slow and end up in cool again, or you can go fast and end up in cool, or you can end up in warm. And here too, you ended up in cool, well, you can go slow or you can go fast. So the same little snippet appears again and again and again and again, and with expecting max, essentially you would check this over and over again. So that's the first problem. The second problem is that actually this tree doesn't stop, right? It just keeps going and going and going and going. We didn't say, car, you have 10 steps and that's all you can do. We said, okay, this is the MDP that you're in, and that every time step you have these two options available to you, and now go and figure out what to do. And so what we're going to see today is that we can actually do something slightly different from an expected max search that gets around these two problems. And really when it comes to, so we're going to do some state reuse for the first problem, that's clear. For the second problem, what we're going to bank on is this idea of a discount that we talked about last time. That if we care less about things that happen in the future, we showed, and if the way we care less is at reward at the next step is only worth gamma as much, like 0.9 as much as if I were to get that reward now, then we were able to actually prove that our total reward from time 0 to times infinity is going to stay not infinite. It's going to be some number that's less than infinity. And that's what we're going to use, essentially, to be able to solve this and not have to go to depth infinity. And to do that, we have to introduce this notion of values. So this is going to be important. We're going to denote this idea of a value by v. And v star, evaluated at a particular state, is going to be a function that gives us, it's going to be the value of, that gives us the expected utility if we were to start in S and then act optimally in expectation. Now, we don't know yet how to act optimally, right? But we can mathematically define this quantity. There is such a thing as acting optimally, and if we started at S and acted optimally for infinite time in expectation, what would our utility be? And we saw last lecture that this is actually a finite number. Again, because if we use a discount, then we have that nice geometric series and it helps us out. So V, and notice that there's a star here. That's because we're going to also, towards the end of this lecture, talk about values when you're not acting optimal or you're doing something else, and those also give you some values. But V star is going to denote, star in this course denotes optimality. V star is going to be the value of a particular state if you act optimally from now on. Now let's jump to the third part here. We're also going to define the optimal policy. So policy was a mapping from state to action. It told the agent, if you're in state S, this is the action A you should take. The optimal policy is the one that maps the state to the optimal thing you should do from that state. That's what the optimal policy is. And now, this intermediary thing here, the second term, we're going to define the value of a Q state as opposed to the value of a state. So we're going to refer to this usually as a Q value. So again, Q states were this intermediary thing. So this was a state, S, but then Q states were if you start in state S and committed to taking action A, what happens then? So we're gonna denote by Q star of SA the expected utility, not if you act optimally, but if you take that action A from the start. And that might not be the optimal action. It might or might not be, we don't know. And then we're gonna reach some new state S prime. And from then on, we're gonna act optimally. So that's what this Q value is. So the value V star says, I'm in state S, what if I start acting optimally from now on until forever? The Q value says, I'm in state S, and I take this action A, which might or might not be optimal, and then from then on I act optimally. And it's going to be a really nice intermediary quantity that we're going to use a lot in the next few lectures. It's just, it turns out it's really convenient to reason about this. And so to see that, who can tell me if I give you Q star as a function, so you can plug in any state and any action and figure out what the value is. If I give you Q star, who can tell me what the optimal policy is? How can you recover the optimal policy, pi star, from Q star? Yeah.
Do you do something recursively, or you start with like almost the goal state and then go backwards? Like, in order to so you know the ending configuration, and then you go backwards until you get to the state that you're at?
Okay, so the suggestion is maybe you go backwards from the goal. The first thing to note is that there is no goal. We just have states, and when we act and transition to new states, we get rewards. Now, you can encapsulate some notion of a goal if there's a state where from that state you have to exit, and when you exit you get some really big reward. You can think of that, maybe conceptualize as a goal, but there's no actual goal. We just have states and actions we can take and transitions. Now, also, I want to point out that recursion is not really, we're going to get to an idea very similar to what you mentioned, but what I asked here was, what if I actually gave you Q star? So Q star tells you if I'm an S, and I take action A, and then act optimally. And I'm not telling you how to act optimally. I'm just saying this is going to be the value of being an S, taking action A, and acting optimally from that on. And now what I want to know is what is the optimal action at S? That's what pi star needs to tell me. If I give it S, you need to tell me what's the optimal action. So what's the optimal action?
So you run Q star for all legal actions, and then just pick whichever action returns the greatest value from Q star?
Absolutely. So the answer was, well, I'm an S, and I need to know which of these actions to pick. And I have this handy thing called the Q star, right? And Q star, the Q value, basically says, well, if I were to take this action, this is how valuable that state would be if I then acted optimally. If I were to take this action, this is how valuable it would be. If I were to take this action, this is how valuable it would be. So to figure out what the best thing to do is, I just compare all of these different values and take the best one. And the best one gives me the optimal action to take. So if I had Q star, which is not a trivial thing to get, but if I had it, I could just figure out what the optimal policy is. Is that the same? What if I have V star? If I have V star, it's not so trivial to recover the optimal policy. Because V star talks about, I could look, okay, I'm in S, and I have all these actions to take, and for each of them, I might end up in all these states. And it's true that I can use the V value, the V star at S prime, right? For every S prime that I could possibly end up. For each action and for each way the world could resolve, I could look at S prime. And in a sense, I could compare actions that way. But I have to do this extra layer of, if I were to take this action, I don't just know what the value is. I have to look at all the possible things that might happen, look at V star, add for those outcomes, average that, weighted by the transition probability, and then that gives me the Q value essentially for that Q state here, and then I can compare them at max. So there's a way to go from, and we'll see this in a little bit, there's a way to go from V star to Q star, but it does require doing a little bit of search, like a one-step expecting max. All right, so let's look at an example. This is an example of the values on our favorite grid world. This was a grid world where this one exiting here would have a reward of +1, exiting here would give you a reward of -1, and there's no living reward, so assuming living reward equals 0. There's a discount of 0.9, which means if I get this reward at the next step, it's only worth 0.9 as much. And there's a noise of 0.2. The noise of 0.2 means when I try to take an action, like if I tried it from here to go right, I might end up there, but I might also end up somewhere else with probability 0.2. So the first thing we see here is that at this state, the top right state here, well, the value is 1. Why is the value 1 here? Well, it's not too hard. The only thing that you can do at that state, by the way we define the MDP, is to exit. That's the only action available to you. And we have this transition function, this reward function that says, well, if we're in that state and we exit, we get 1. So that's the only possible thing that we can do and that could possibly happen, so the value there is 1. The value here is -1 also because you're forced to take the exit. So if you fell into the pit, then you're kind of forced to incur that -1. There's not much else you can do. Why is this 0.85? And in particular, why is it not 0.9? So you might argue that if you're in this state here, right, the optimal thing to do is to try to go here where there's going to be reward. And you have a discount of 0.9. So you're going to be in that state. You're going to try to go here. And if you end up here, then you're going to be able to take the exit, and that gives you a reward of 1. Now, there's a discount of 0.9. So you'll think from that, from where you're sitting here now, that's 1 step into the future. So that's going to be a value of 0.9. Why is it 0.85 and not 0.9? Yeah?
I'm guessing the noise equals 0.2, so that there's a 0.2 chance you're not going to actually successfully go that direction.
That's right. It's because of this damn noise, because we're not in a search problem, so we can't actually rely on our actions taking us there. If there was no noise, if noise were 0, then of course you would go here, then you'd know that you could take the exit, you collect that reward of 1, so overall this state would have a value of 0.9. But the problem is that when you try to go there, you know, your wheels might turn slightly differently and whatnot, and you might actually find yourself either going here or trying to go there, but you can't go there, so you'd stay in place, right? So this 0.85 accounts for that possibility as well. That's absolutely right. So those are the values, V star. Now let's look at Q star. So what you see here is now for every state, we don't have just one value, right? Q star talks about what happens if I'm in a state and I take a particular action and then I act optimally from there. And so you'll see the 0.85 here that corresponds to the optimal action of trying to go right. So that's the value of that state, and you'll see it as one of the possibilities. But then you also get Q star of being in the state and taking the action left. That's not the optimal action, but that's still associated with the value, because you can say, well, if I'm in this state and I go left, what might happen? I might end up here, I might end up here, or I might stay in place, and each of these are associated with some values, meaning if I start acting optimally then, until time goes to infinity, how much expected reward do I get? And so that's how you get the 0.66 here. And similarly, this is kind of an interesting case here, minus 0.6. Well, why is that minus 0.6? Well, it's minus 0.6 because here that is associated with you're in this state and you try to go right. Jump into the fire pit. That's what you try to do, right? And if you jump into the fire pit, if you actually get to the fire pit, then you're forced to take the exit and get this negative reward minus 1. But there's also some chance that you won't end up in the fire pit, right? And so there's some chance that you'll go here or you'll go here. And Q star says, okay, you're going to take this really stupid action, this one here, and then you're going to act optimally. So if you take this really stupid action and you actually accidentally end up here and then act optimally, you have a value of 0.85. Okay, so that's why that minus 0.6 kind of takes into account all these possible things that might happen. Where again, we might take an action, it might be stupid, and then we might end up somewhere, and from there on, wherever we end up, we're going to act optimally. Those are Q values. All right, so now this is probably going to be the most important slide of all of MDPs and reinforcement learning and everything. We're going to go through something called the Bellman Equation. So let's try to stick together and understand this very well. So it turns out there's a property that values might have to satisfy. And in particular, we're going to start easy. We're going to start with what we discussed already. We're going to say, if I want to know V star of S, and I have access to Q star of S, evaluated at any action I might want to, then all I need to do to compute V star of S is to do what? You already said it. Can you repeat it? Yeah, take whichever one gives you the maximum one, right? So V star of S, the best thing, the V star of S, which is the expected utility if you act optimally forever, is going to be equal to the maximum Q value that you could get from that state. So you look at every action, and the Q value says, well, for each action, if I then start acting optimally, this is how much I get. So if you want to start optimally from the beginning, you just take the best action, and that gives you the value of acting optimally from that state S. Is everyone okay with this? Any questions about this particular equation? Good. Now we have to start reasoning about what this Q star is, because no one gives us that for free. So if I'm in a Q state, so if I'm over here, I was in state S, and I've taken action A, and now I don't know what's going to happen. Any of a number of things might happen. But if someone were to tell me what's going to happen, if I knew that I'm going to end up here, if I have some sort of magic oracle that tells me I'm going to end up in S prime after this, then what would be Q star of S of NA? Well, the first thing that will happen is I'll actually get some reward out of that transition, right? So the first thing is I'll incur the reward associated with being in state S, taking action A, and then I'll end up in S prime. So good, so I collected that. And now I'm in S prime. And from here on, if I act optimally, because that's what Q star tells me to do, take this action A that might be stupid, but then act optimally. If I act optimally, I'm going to get V star of S prime. And the only trick here is that this is actually going to be discounted because it happens one step in the future. And of course, I don't know S prime. I don't actually have an oracle. But what I have is a transition function that tells me what might or might not happen. So I can actually look at this value, which is the reward I get from my current action, plus what I expect to get if I act optimally from then on. I can look at that, and I can average that across all possible things that might happen, all possible S primes. So I can sum over S prime. I can look at the probability of ending up in S prime, given that I was in S and I took action A, which is what my Q told me to do. And then for each of these possibilities, I know that if I did end up there, I'd get my reward, and then I'd act optimally, and I'd get V star of S prime. Okay? So essentially, V star depends on Q star, and Q star depends on V star at, a bunch of other states. It's a recursive definition. It doesn't yet tell us how to compute this. It's just an equation that needs to be satisfied if V star is what we actually said it is, which is the value of how much reward do I get in expectation if I act optimally. And Q star is what we said it is, which is if I am in this state and I take this action and then I act optimally from down on, how much reward do I get in total? Yes?
Can you repeat what's the T?
What is the T? So the T here is our transition function in the Markov decision process, and it is equal to the probability of S prime given S and A. So if I'm in S and I committed to taking action A, I find myself at this Q state here, and from this Q state, I don't know what's going to happen because I control my actions, but I don't control what the world does in response to my actions, right? I might slip, who knows? My wheels might turn in the wrong way, and so on. So the transition function T of S, A, S prime assigns some probability to all these possible outcomes. Okay, so that's the probability of ending up at S prime given that you started in S and took action A. Okay, so that gives us some probability for this S prime, some probability for some other S prime here, some probability for some other S prime there. Okay, and then all we're saying is that for each of these, and they're weighted by some probability that the transition function told us, for each of these, when I started in S and I took A and I ended up there, right? Basically, I will have gathered this reward right here, and then I'm assuming by the definition of Q star, I'm assuming that I'm going to be optimal from then on, from S prime, whatever this S prime is, and that means that that has a value of V star of S prime by the definition of V star. Yes?
Because
It is kind of like expectimax in that you can think of these equations as kind of reasoning through one step of expectimax and looking at the evaluation function to be V star, right? And that's just by the very definition of V star. Yeah?
So R is like, is that like getting the reward for eating a pellet or something? Like if you eat a pellet and then you get something, you go, like that's prime.
So that reward could be the living reward, is what we define it in the grid. So every action that you take has some cost. It could be that you encounter upon some really good state that you like to be in, and so then you get a high reward. It could be like you ate a pellet, depending on what your definition of state and so on is, right? So the reward function just captures what makes a transition good. And it could just capture what makes a particular state good. It could, like R is depending on S, A, and S prime. So it could literally depend on those three. They might all need to come together. It could depend on just S and A. In other words, I might have a cause for taking an action, and particular actions for particular states might be more costly, but it doesn't really matter what I end up. It's just like I still paid that cost. So it could just depend on S and A. Or it could depend just on S, it could depend just on S prime, it could depend just on A or whatever. But in the most general sense, it's something that depends on S, A, and S prime and associates some reward or some cost to taking that action in that state and ending up at S prime.
What's the symbol before the V star?
And what's the symbol before V star? Great question. So this here is a gamma. It's our discount that we talked about in last lecture. And when we basically said, well, we need a way to differentiate, we need a way to capture the fact that the world might end, disaster might happen, sort of outside of what our MDP dictates, right? We might just die at every point. So we need a way to capture that. We said that there's a 1 minus gamma probability that that might happen, which means that the reward that I get after one step is only worth gamma times as much. So if gamma equals 0.9, the reward that after one step is worth 0.9 as much. Reward that you get after 2 steps is worth 0.9 squared as much, and so on. That was the discounting. So that's gamma. Any other questions about this? It's a really important formula, so I want to make sure that we all understand this. I'm going to come back to it over and over again. So now we can put this into one single mega equation that only talks about values. All that we did here is we took this V star to be the max over A of the Q. So here's the max over A. And we plugged in this as Q. Right? So now basically all this says is, well, if I'm in S, what's the value of S? Well, I have one step to take, and it better be optimal. And then I'm going to act optimally from then on. So I can define it in terms of the value of where I end up, discounted plus something by gamma, plus the reward that I get by taking that action from that state and ending up in S prime, and weighting that over all possible S primes, and doing this as a max over all possible actions. It's a recursive definition of reward, of the optimal value. Sorry, it's a recursive definition of the optimal value. It doesn't tell us how to solve this. It's just what needs to hold true if this is actually what we define it to be, which is the optimal value. Any other questions about values and the Bellman update? Yes, a question over there. Did you ask if T is the cost?
Of the transaction.
No, it's the transition function. It's the probability of getting to state S prime if you started in S and took action A. Okay, so that's the Bellman update. And note that it doesn't tell us how to actually solve this, right? It's just a description of what needs to happen if we have optimal values. So in order to actually solve this, we're going to use an idea that you hinted at earlier. So we're going to kind of go work backwards in time, so to say. We're going to say, what if I only have one step and then the game ends? What should I do then? And then we're going to say, all right, well, what if I have 2 steps? What should I do then? And we're going to use what happens if I just have one step to figure out what we should be doing if I have 2 steps. And then we're going to say, what if I have 3 steps? What should I do then? And 4 steps, and so on, until we converge. That's going to be how we actually compute these values. And let's go in more detail of that. So first of all, we have to define something called time-limited values, which is this idea. We're going to call it V sub k of s. It's no longer going to be V star, which V star actually assumes that you're going to act optimally for infinite time. It's going to just be the value of acting optimally if the game actually ended in k more steps. So we're introducing this quantity, we're calling it V sub k. What happens if I only have k more steps and then time runs out and everything is done? What should I do from this particular state? And how should I act optimally? And this value here, V sub k, captures the value, the expected utility of acting optimally if I started in S and only had k more steps to go and I acted optimally. So this is really like a limited depth expecting max. So you can imagine for k equals 2, we start off in the initial state, which is cool, and then we draw out the search tree for depth 1, and then we draw it for another depth, and then we stop there. The value that we would compute at this top node here, that is V2 of that state. To do this in expecting max, we had to use an evaluation function. We had to, because we wouldn't actually stop after 2. We would just sort of do our search for depth 2 and then use some sort of approximation, some evaluation function that tells us how good each of these bottom states, these leaves are. But now we don't need that, because the way we've defined this is that the game is literally going to end after this. So we're just going to count the rewards we've gotten this far, and that's it. Okay, so that's V sub 2 of the being in cool. Here's an example. So when k equals 0, V sub 0, everything's 0. All the values, all V zeros are 0. Why is that? Well, how do we define, did you have an answer? Yeah. The game doesn't even start. The game's already done, right? There's nothing you can do. You don't have time to do anything, to take any action at all. So you didn't gain anything. You didn't lose anything. 0. OK. Now, when we go to k equals 1, so we ask ourselves, what's the value of each of these states if we only have one step that we can take, one action that we can take? If we go to k equals 1, will this value here in the bottom left change, or will it stay 0? Stay 0. Why? Well, because if we only have one step, we might take an action, we might go north, we might go right, but who cares? Because we're not going to get the living reward, by the way, I forgot to say, we're keeping that as 0, like in the previous example. So we're not going to gain anything, we're not going to lose anything, there's nothing we can do. What about over here in the top right? Is this going to change or stay 0? It's going to change, because when we're there, we have to take the exit action, and we have time to do that now, so we have one step, and we can get our reward of 1. OK. What about over here? Is that going to change or stay 0? It's going to stay 0, because I have time to take an action. I have time to get myself into this state, but I don't have time to then take the exit, right? So I can't really get anything. It's still 0. So here it is. And by the way, if I am in the pit, I'm forced to take the action and get the exit and get -1. So those are V sub 1 values for all of these states. Now what's going to happen when we go to 2? Is this going to change or stay 0? Did I miss something? Who wants to enlighten me? Wait, what? Oh, someone just stepped in. All right. See, this is the disadvantage of not being there. I have to stand out here and I miss all these things. All right. So when we go from k equals 1 to k equals 2, does this change or does it stay 0? It changes, because now I can I have time to go over there, to try to go over there. I might not succeed, but I have time to try to go over there. And then take the exit. Why is this 0.72? What is it equal to? You have an answer? Yeah.
It takes into account like the discount for getting to the actual end state and then also the noise in that account.
Right, it takes into account the discount and the noise. So if I'm here and I have only 2 steps allowed, right? K equals 2. Then of course I can try to go right, and I will succeed with probability 0.8. And if I do go right, then I have time to take an exit, which with probability 1 will give me a reward of 1, but now it's discounted, so it's 0.9. So I get 0.8 times 0.9. I also have probability of 0.2 of ending up somewhere else, and if I end up somewhere else, then I don't have enough time to then go to that state and then take the exit. So those all have values of 0. Okay, so that's why this is 0.72. I think it is equal to 0.8 times 0.9. Now, when we go to 3, we start having time to do more. And notice that this value here, when we go from k equals 2 to k equals 3, increases. Why did it increase? Yeah, over there.
There's more chance that if you don't go to the reward state, you can go back there at a later point.
So that's a good suggestion. Basically, the suggestion was that now there's a chance that if I try to go here, but I do end up, say, here, right, I can go back. And the general way of stating that is now there are enough time steps left that I can actually do something that could potentially have some chance of getting me reward at whatever other states I might end up, some of the other states I might end up. Yes? So if I take this and end up going down, that's 1 step. Then I try to go back up, that's 2 steps. And then I go, that's a good question. So let's see what happens. So here it works out because I have 2, so I have time and yeah. Yeah, that's very good, very good. So it's true that if I end up here, I still don't have time. That was a very good observation. And then what happens is that there's some chance that I'll actually end up trying to go up. Well, not trying to go up, but as a consequence of going to the right, the action will resolve in me trying to go up, banging against the wall and staying put. And then from there, I still have time to do something. Very good. All right, so that's k equals 3, k equals 4, and so on and so forth. So at some point, this is after 10 iteration, 11, 12 iterations, and then after 100 iterations, it looks also very similar. Question, yes?
How come k equals 2, the square next to the negative 1 didn't have value? Couldn't it like accidentally go to the negative and then be forced to take the exit?
So the question is, how come here we don't have a value when k equals 2? Well, because if I try to act optimally from here, I don't try to go into the fire pit, right? Maybe the best thing to do here is to try to go to the left. And if I try to go to the left, I basically either stay in place or end up here or end up there. If I end up here, I don't have enough time then to still go here and collect the reward, so I stay at 0.
The noise can't accidentally make you go to the negative 1.
Right, so the way we define, this is just the property of how we set up this particular grid world example in the beginning. We said that there's a 0.8 chance, if you try to go forward, there's a 0.8 chance that you actually go forward, 0.1 chance that you go left, 0.1 chance that you go right. And there's no chance of going backwards. If we had a chance of going backwards, then you're absolutely right. Yep, good question. All right, so this converges at some point. If we go back to this tree here, then what we see is the following. We see that there's a lot of computation that we're doing over here, but really all of these are v sub zeros. Everything that happens one layer up is v sub 1, then it's v sub 2, and so on. And so we can actually reduce a lot of computation by just computing these v sub k's instead of running through the whole tree and branching out everything. And that is the idea behind an algorithm called value iteration, which is kind of the most classic algorithm for solving MDPs. And we've essentially seen it already. All that value iteration does is it starts with v sub 0, and then it says, well, at every iteration, if I want to compute v sub k plus 1, well, all I need to do is run my Bellman update. I maximize over actions like I did before. I take an expectation over possible outcomes that action might resolve into. So that's the sum times the transition probability. And I get the reward. And then I'm going to be in S prime, and I'm going to have k more steps to go. Because this, I was in S, and I had k plus 1 steps to go. So this here is going to be v sub k of S prime. And you just repeat this over and over again until convergence. We'll talk in a little bit why it converges. But does that make sense? I basically say, well, if I have k plus 1 steps to go, I'll figure out what my options are for this first step, and then I'll have k more steps to go. And if I already computed what's the optimal thing for if I have k more steps to go, now I can actually start reasoning about, well, what if I have one more step additionally? What should I do then? That's the idea of value iteration. It's just running the Bellman update. And you repeat this until convergence. What's the computational complexity of every iteration as a function of the number of states and the number of actions? Well, what does this do? First of all, we have to compute this at every state. Okay, so we have to compute v sub k plus 1 at every state. And there's S number of states, capital S number of states. Then we look over all actions. So we have to consider all possible actions, and there's capital A of them. So we're already at S times A. And then for each of those, we look over all possible states that I could end up in. In the worst case, of course, your transition function might give 0 probability to many of these, so you might not look at them. But in the worst case, you are at a state, you take an action, you might end up anywhere with some probability, and you look at all of those. So the combinational complexity is S times A times S, where S is the number of states and A is the number of actions. At every iteration, I do S squared A work in the worst case. So it's pretty expensive. It's expensive because it's squared in the number of states. And if you know anything about robotics, then we start talking about the degrees of freedom that the robot has. Like, for instance, if you have an arm, it might have 6 or 7 degrees of freedom. And if you look at the dimension of the state space, well, the number of states is exponential in the number of degrees of freedom. And then if you square that, you're quite in a bit of trouble. So it's not a cheap algorithm to run. But there's a theorem that says that it will actually converge eventually to the optimal values if you keep doing this. And before we get to that, let's look at a quick example. So very, very quick example before we take a break. In this racing MDP that we talked about before, we start out with v sub 0, and we saw all of these are 0 because there's nothing I can do. And then what's v sub 1? Well, let's compute v sub 1 for the cool state. If I'm in the cool state, I can either go slow or go fast. And if I go slow, I'll get a reward of 1 by just the way we define this MDP, and I'll stay in cool. So when I look over this max here, the slow option, this guy, all that's left after the max evaluates to 1. If I decide to go fast, then I have half a chance of getting reward plus 2 and then staying in the cool state. And if I stay in the cool state, well, that's V0, which is 0. And I have a 0.5 chance of getting my immediate reward plus 2 and then ending up in the worm state, which if I only have 0 steps to go, that also has a value of 0. So the fast option, which I wrote down here, has 0.5 chance of getting plus 2 and 0.5 chance of getting plus 2 the other way. So overall, the value of that evaluates to 2, and the value of the state is going to be the maximum of the 2, so that's going to be 2. Now let's do it for the red state, just for kicks. For the red state, if I'm in the red state and I have one more step to go, I can go slow. And if I go slow, I have half a chance of getting a +1 and staying cool, half a chance of getting +1 and going cool, it's half a chance of getting +1 and staying warm. So that's 0.5 times 1 plus 0.5 times 1, that's 1. That's the Q value of being in state warm and taking the action of going slow. If I'm in warm and I decide to go fast, well, the Q value is -10. I just overheat with 100% chance, and I get -10. So the best out of these two is 1, so that's the value there. And then for overheating is 0, there's nothing you can do. Now for V2, now I have 2 steps. What I'll do is I'll reason 1 step ahead, and then I'll use these values V1, like our equation said. So let's see. I am in cool. Again, if I am slow, I'll incur a reward of 1. And if I incur a reward of 1, I'll end up in cool, and cool has value of 2. So that will be 1 plus 2 equals 3. If I go fast, I have half a chance of getting +2, staying in cool, and then in cool I have a value of 2 for 1 more step. Or I have half a chance of getting +2, going to warm, and in warm I have 1. So that's 0.5, 2 immediate reward, 2 the value of cool, plus 0.5, 2 immediate reward, 1 the value V1 of red. So essentially that's how you go through and reason through this. You build up from V0 to V1 to V2, and on each step you use the previous values that you computed. And let's take a quick break before we talk about convergence, because it's already 12:03. What's the value there? We already computed that. You can think of it again as, well, what are the options I could take, and then I have 0 steps to go. But we already did all that work when we computed it before.
Yeah, so each option we add them all up. You just apply this formula. You use the B sub.
Yeah. Yeah. You use B sub K. Did you have a quick question? right, let's get started again. So essentially, all that's happening here is we're saying, if I have one step left, what can I do? And I compute the value of that. And then when I have 2 steps left, I ask, well, what can I do at the first step? And then I'll know that I'll have 1 step left. And of course I could say, well, what can I do at that 1 step? But I already computed that under V1. I already did all the work to say, when I have only k more steps, when I'm at k plus 1, if I have k more steps, what do I do? So it's a dynamic programming approach. Why does it converge? Well, you know, it doesn't always converge. It converges if you have really a finite time horizon. That's obvious. You only have to go until some limited k. It also converges if the discount is less than 1. So if you actually do discounting and you have a gamma less than 1, essentially the way to see this is when you go from v sub k to v sub k plus 1, you're adding another layer to your tree. In that layer, you're going to have some rewards. Those rewards are somewhere between the minimum reward and the maximum reward. And those rewards are going to get discounted by gamma to the k. So in the limit, they're not going to matter that much, and that's why you're converging. That's the intuitive way of understanding convergence. Good, so that's a way to compute these values. Now, what do we do with them? If someone gives me these values, or I run value iteration, I get these values, how do I know what to act? How do I know in each state what the optimal action is? And it's not obvious. I'm going to claim that if this were a deterministic problem, in other words, if my transition function plays probability of 1 to one of the states and probability 0 to anywhere else, then it'd be trivial to figure out how to act. How do I act in a deterministic problem if I give you the values and I ask you, okay, in this state, what's the optimal thing to do? What would you do, knowing that you're actually in control of the effects of your actions? So the current state tells you what the expected utility is if you act optimally from now on, right? And then you can look nearby, and all the nearby state values will tell you what you get from there if you act optimally from then on. So all you need to do is look nearby and pick out the one with the highest value and go there, because you're in control of our actions. So you look at your neighbors, you look at for all actions, where you're going to end up, you look at the values, and then everything's great. The problem that we have now is that we're not really in control of the effects of our actions. So we have to take some expectations, but that's not a big deal. We've done that before. So if I want to know, if someone gives me the values V star, and I want to know, okay, if I'm in action S, what action should I take? Well, all I need to do is look at all actions, maximize over them, and essentially compute the Q value. Compute if I take that action, for every state S prime I might end up in, well, I'll get that reward, and then I'll have the value from the new state S prime. This, again, looks a lot like the Bellman update, right? But it's something called policy extraction, and it's a way to figure out what the optimal action is backwards from having gotten the values. And again, note that if you knew S prime, you wouldn't have to sum over this, would be in a deterministic world. And all you'd have to look at is, okay, for every action that I can take, where do I end up, what's the reward there, and what's the value from there? Yes?
What is R?
What is what?
R.
Oh, okay. So pi star of S. Pi star is a policy, so it's a function that maps states to actions. So pi star of S returns an action, okay? So far we talked about values, and we were taking maxes over actions, because the max over some entity, you know, gives you a value, and that value is the value V star. Now we're looking at, we wanted to return an action. So the argmax or the argmin, these are mathematical operations that essentially return the argument, in this case the A, that minimizes or maximizes that value. It's a very good clarification question, thank you. So we're looking for the action, this is going to return the action that makes that maximum happen. Okay? So that's how we extract the policy. if we know the values. And so essentially the way we solve MDPs is we do value iteration, like we talked about before, we get some values, then we do policy extraction, and we know the optimal policy, and then we can just, this is all in simulation in the agent's brain, right? Because it has this model of the world and how the world looks like. And then when the agent actually starts acting, it directly acts using the optimal policy, pi star, that it recovered through this algorithm. Now, if someone gave me the Q values, like we discussed many, many times before, I'm in good shape because if I have the Q values here, all I need to do is figure out which action corresponds to the higher Q value, and that's what pi star of S is. It's just the arc max over A of the Q value, Q star at S and A. That's just the action that puts me in the best position going forward. Okay, so the lesson here is that if you have Q values, it's much easier to extract policies than if you have just values. And that wraps up value iteration. Now for the next 10 minutes or so, 10, 15 minutes, we're going to talk about a different algorithm. Like I said, value iteration is kind of the most canonical thing that you learn about when you learn about MDPs. But there's also a method that doesn't directly work on values, but it works on policies. And this kind of should take you back to what we talked about in constraint satisfaction problems, where at some point we're like, okay, well, we can build up this assignment, or we can just say, let's start with some assignment, and then at every iteration, make it better, make it better, make it better. Now we're going to do the same thing for policies. We're going to start off with a policy, and then we're going to iteratively make it better through something called policy iteration. Now, the nice thing here is that it turns out that that's actually optimal. Local search wasn't optimal. It could get stuck in local optima. In this case, the particular way we're going to be doing local search here is going to guarantee that we converge to the optimal solution. All right, so this is motivated by some issues that that value iteration has. So value iteration keeps repeating this equation, this Bellman update over and over again. And of course, we already talked about this. It's slow. It runs in S squared A. The second problem is that it actually reaches, the policy itself converges long before the values actually converge. So because the policy looks over a max over values, and that max changes less often, so to say, than the way the actual values change. And so policy iteration kind of capitalizes on that. So here's value iteration after 12 iterations. And then here's value iteration after 100 iterations. And notice that, yes, the values changed slightly, but the policy stayed the same. So kind of people looked at this and said, why do all this work? Is there a way to just kind of stop when the policy converges? And so policy iteration is an alternative, and it runs in two steps that we're going to quickly talk about. The first step is we're going to start out with a policy, and we're going to iteratively do these two steps. First, we're going to evaluate the policy. So we're actually going to compute values based on that policy. And the second step is going to be we're going to use those values, kind of locally fix the policy. And then we're going to repeat. We're going to evaluate, get the new values, locally fix it, and repeat and repeat and repeat. And we're going to talk about how to do both of these steps. We'll repeat these steps until convergence. And it turns out if you do this, it's still optimal. And in some cases, it converges much faster than value iteration. Good. So two steps, policy evaluation, policy improvement. For policy evaluation, okay, so let's take a step back. So far, we talked about kind of diagrams that look like this, where we're starting at some state. Wow. We're starting at some state. We could take a number of actions, and we were reasoning about all these possible actions that we would take. And then we would end up in some new state S prime. Now we're going to talk about what if someone actually gives you a policy. So you start off with some policy. What if someone actually gives you that policy? What do you do then? Well, if someone gives you a policy, you don't have to any longer look over all possible actions. The policy tells you, by the definition of a policy, what action you should take. So you end up in something, and then you end up in a Q state, and you still have to reason about all the possible things that might happen, how the world might resolve that action that this policy told you to take. So that's the notion of fixed policies. And we can define now the utility of a policy. So that's going to be yet another V thing, right? So we talked about V star. That's the optimal policy. That's the optimal value if you have infinite time steps to go and you're going to act optimally. Then we talked about V sub k, which is what if you have only k steps left, okay? If you act optimally for those k steps, what's the value? Finally now, a third concept, V superscript pi. So that is going to tell us if I give you a policy pi and you follow that policy instead of following the optimal policy, what reward are you going to get in expectation? That's V pi of S. And the way we can define V pi of S is again through our favorite equation, except now, notice that the max is missing. Normally when we looked at the Bellman equation for V star, we had to look over the max over all the actions we could possibly take and then compute an expectation what would happen. But now we're looking at the case where someone actually gives us a policy. And so all we're asking is if you follow that policy, what will happen in expectation? And so there's no more max anymore. We're not maxing over some action A. We're actually plugging in pi of S. So the action that the policy that someone gives us tells us to take when we're in action S. And so there's a recursive relation here where you can start evaluating V pi of S. And essentially what we're going to do is we're going to do value iteration to compute values for this policy, except we're not going to have maxes anymore. But everything's going to look very much like value iteration. So here's an example of what that might mean. You have here two different policies. One of them says always go right. It's a pretty dumb policy. It's not the right thing to do. And one of them says always go forward, which seems like a much more reasonable thing to do. If you look at the values that they have, well, you can still compute values for each of them. It's just that the values for the thing on the left are going to be much lower because it's a really dumb policy, so you're not going to get as much reward out of following it, right? So, whereas if you always go forward, then everything looks much nicer. So that's kind of the thing with policy evaluation, and the way we're going to compute it is we're going to start off with 0 values like we did in value iteration. And then at every iteration, we're essentially going to do value iteration, but instead of the argmax, we're just going to follow pi of S. So that basically, this equation here tells us if I'm in state S and I take the action that the current policy tells me to take, well, what will happen? Well, I don't know exactly where I'll end up, but I'll take an expectation. That's the sum here times this transition function that everyone loves so much. And then that's going to take me to some S prime, and then from that S prime, here I might have some reward that I get out of that transition, and then I have V sub k pi, which is from S prime, if I keep following pi, do I get in expectation? So this is just like value iteration, except we're not leaving the actions as a variable, we're following this particular policy. The efficiency of this is S squared because we're no longer looking at actions, right? So before it was S squared times A, now it's just S squared because we're actually evaluating this for a particular policy. All right, so policy iteration basically starts out with a policy. It evaluates, it basically runs this kind of pseudo value iteration to evaluate how good that policy is, to evaluate the values induced by this particular policy. And once we have that, we start improving the policy. Because once we have the values, we can do a one-step look ahead and say, well, okay, at the previous iteration I had pi I. And at pi I, when I applied it to S, it just gave me some action to take. But now I kind of can look ahead and say, maybe I can take other actions, and for each of these actions, I'll have a distribution over states, and I'll get some reward, and then I'll follow pi I from then on and get the value of following pi I. So what I can do is I can actually max over these actions, right? I don't have to keep on following pi I. I can do just this one-step look ahead that says, what if I act kind of optimally, I actually maximize over my actions now instead of blindly following pi I, and then start following pi I afterwards. That's the idea of improvement. It doesn't fix the whole policy altogether. It doesn't do a 2, 3, 5K step look ahead. It just does this one step look ahead and says, okay, well, if only for this one time step, I try to do something better, and then I kept following the old policy, what would happen? And that gives you a new policy, because for every state, you'll now have a better action to take. And then you compute the values induced by that state using policy evaluation, then you improve that policy, and so on and so on and so on. And that's what policy iteration does. Now, they both essentially compute the same thing. They compute optimal values. In value iteration, every iteration updates both the values and kind of implicitly updates the policy, because you can always do policy extraction. And we don't explicitly track the policy, but taking the max over actions implicitly does this recomputation of the policy. In policy iteration, where we start off with a policy and iteratively improvement, basically we do several passes that update the utilities with a fixed policy, so we take our current policy and essentially run like a mini value iteration where we don't do R max over actions, but we still have to do a bunch of iteration until convergence. And that evaluates the policy. And then you start improving it. The new policy that you get will either be better or you're done. The policy stayed the same, you converged. All right, so both are DP, dynamic programming ways of solving MDPs. It's just kind of a matter of, do I look at my values, compute my values, and then extract the policy, or do I start off with some policy and use that policy to compute values and then go backwards? Yes?
So policy evaluation takes S squared, right?
Policy evaluation takes S squared per iteration.
And then we do it 8 times for each improvement, right?
And then you do it for each iteration. So basically now every iteration, so that's kind of the second part of policy iteration, right? Because for every iteration of policy iteration, you have to do like a simplified version of value iteration, right? You have to run that until convergence and then improve. And then you run that until convergence and then improve.
So would they have the same practice?
In practice, it turns out that because for problems where the policy converges much faster than the values, you can actually detect that and kind of declare success earlier, whereas your values wouldn't have converged yet. So in practice, people have noticed that there are a lot of cases where this happens, and so a lot of people end up using policy iteration instead of value iteration. But certainly value iteration is sort of the canonical, first you understand value iteration, and you really make sure that that makes sense. And then you start thinking of, well, okay, maybe policy iteration is a slightly different take on the problem that might be better in some cases. All right, so to sum up, we're looking at Markov decision processes, and regardless of kind of what you want to do in these, it comes down to some version of the Bellman equation, right? So in some cases, we use the Bellman equation to just write down the characterization of what happens when things converge, so V star as a function of V star. In some cases, we looked at writing it out in terms of these steps. Okay, Vk plus 1 as a function of Vk. What happens if I have k plus 1 steps to go as a function of just having k steps? In some cases, we looked at using it just to evaluate a particular policy where we don't have the maxes anymore, and so on, right? But the core idea is the same. The core idea is I always think of, well, right, I have these actions to take. If I take these actions, I end up in a Q state. And from a Q state, there are a number of things that could possibly happen, and I take an expectation over those. And then I end up to a new state S prime where I actually know something because I pre-computed that already. Those are Markov decision processes. Next time, we're going to start talking about reinforcement learning. And what reinforcement learning does is kind of magical. It's still Markov decision processes, but it's Markov decision processes where the agent doesn't know up front what the transition function looks like and what the reward function looks like. So it actually has to go. It can't just pre-plan everything, because that's not going to work. It doesn't know anything about how the world works. It has to go out into the world and explore and learn about it in order to figure out how to act. That's reinforcement learning. Next 2 lectures. See you on Thursday.